In this lecture, we will talk about deadlock. This is a condition of a system where the processes have been suspended because there is competition for the resources that are available to a computer system. So the agenda for this lecture is we'll begin talking about what a deadlock is. We'll try to answer the question whether there is a live lock. We'll take an example and we'll try to draw comparisons between a deadlock in a computer system to a real world example. Next, we'll talk about four necessary conditions for us to have a deadlocked system. After that, we'll talk about resource allocation graphs or RAGs, which are graphical representations of a situation of the allocation versus the requests in a system for processes and resources. And by looking at it graphically, we can assess that particular situation and comment about whether there is a deadlock or not. And we will conclude this lecture by talking about how we go about handling the deadlocks. Can we do a deadlock prevention? Can we do deadlock detection? And if we are able to detect a deadlock, can we do the recovery? So let's start talking about what a deadlock is. So if there are several processes in the memory that are currently getting executed by a processor, they would probably need resources. And if there are several processes in a multi-programming environment, then they would essentially compete for those resources, whether it be memory, whether it be CPU cycles, or it be certain input-output devices. So if resources are unavailable, then process would enter the waiting state. And this could happen to one process, or it could happen to any process where it goes to the waiting state. And it happens when it is doesn't have the resource to complete that process. And sometimes a waiting process is never able to change state, which means that it was waiting for a resource, it wasn't available, so it went to the waiting state and it never became available, so it stayed in that waiting state for a long duration of time. It was never able to change state. The requested resources, if they are held by other waiting processes, what is going to happen? We are going to have a cycle, a deadlock cycle in that case, because one process is waiting for another, is waiting for another, is waiting for another, and the loop comes back to the first process. In that case, when we have a waiting cycle, the progress of the system will be suspended because of that, because no process is going to get the resource it's waiting for, and that particular condition is called a deadlock state. The progress of a system could also be suspended using during livelock, but livelock is a little bit better because the processes that are livelock can change state but without progress. So there is no progress, but they are able to change state. So for example, if a process is waiting for a certain favorable event to happen, then in that case it will go to the waiting state, and when that event occurs, it will come out of that waiting state. So the progress was stopped, it was suspended, but it was waiting for certain favorable event to happen. And we were allowing the process to change state from running to waiting back to the ready state. So live lock is similar to deadlock, however, it can change state. So those are essentially what they are, and let's now take a look at a deadlock example. So there's a lot of debate about whether this is true or not online. However, for the sake of this discussion on deadlock, it serves a good purpose. So there was a law passed, allegedly, or maybe it was just proposed by Kansas legislature in the early 20th century, that when two trains approach each other at a railroad crossing, both shall come to a full stop, and neither shall start up again until the other has gone. And as you can quickly see, it is absolutely illogical, because we are never going to have a situation where either of the trains will be able to move if they were following this law. So that is a very good comparison we can draw with a real world scenario like this to a deadlock state that could happen in a computer system. So the resources are the problem. Every process is competing for a resource, which is competing, and the resource is being used by other processes. So that waiting state could be in a cyclic loop, and that would mean that no process will be able to progress, and the system will stall. So to understand this better, we are going to try to understand when we get into this deadlock state, how do we prevent it, how do we detect it, so that we can design computer systems better so as to stay away from this deadlock condition. So let's start talking about a system model. A system consists of resources, and we are going to name the resource type as R1, R2, and so on to Rm. So there are M resource types here. These could be CPU cycles, memory space, it could be IO devices. A resource is any resource for a computer that a process might be interested in using. And then each resource type, R sub I, can have W sub I instances. So for example, we may have multiple IO devices of the same type. So Ri, those are your resource types, and W sub I is the ith resource type related instance. And then each process utilizes a resource as follows. First, it will request for a resource, and once it requests for a resource, the operating system will have to assign an instance of that particular resource to the requesting process. At that time, once the instance is granted, the process can use the instance of the resource, and after it is done using it, it will essentially release that instance of that particular resource so that other processes can use that instance. So request, use, and release is going to be the what the process does with a particular resource, and the operating system will have to manage each of those steps. So let's try to characterize the deadlock condition, and we are going to use four terms over here. These four terms correspond to four necessary conditions that need to be held simultaneously in order for us to guarantee that there is a deadlock. So for example, if one of them happens, then the chances of a deadlock are going to be there, but we are not going to be able to say for sure whether there is a deadlock or not. So all of them simultaneously, when they are true, then we can say that the deadlock will certainly be going to happen. Mutual exclusion. Mutual exclusion means only one process at a time can use a resource. So one resource instance per process. So you will have one IO device, you will have one memory space that you can access, you will have one CPU cycle that you can ask for. So only one resource type, or I should say the resource instance for that particular resource type that I can use for one process. So they are going to be mutually exclusive. Now, how can I think about it in terms of resources? Well, this is going to be the case when you have resources of the type non-shareable. So if I cannot share a resource between multiple processes, then that is going to be classified as a non-shareable resource, which is essentially this. Only one process can use that resource at any given time. So if you have that particular situation, then the chances of a deadlock will increase. The second condition is hold and wait. And we consider a process to be in this hold and wait state if it is holding certain resources and it is waiting for certain other resources. So a process holding at least one resource is waiting to acquire additional resources held by other processes. So that's a hold and wait condition. And if it is true, clearly you can see that the chances of a deadlock will increase. It is not guaranteed though, because the other processes may be able to finish, they might be able to release the resource, which can then be used by the current process, so it will be able to make progress. So this is not guaranteed. However, the chances of a deadlock will increase if there is a hold and wait condition. Next, no preemption, so no kicking out. A resource can be released only voluntarily by the process holding it. So that means that once a process acquires a resource, nobody can take it away from it unless it voluntarily gives it up. So there is going to be no preemption. So the operating system cannot come in and say, I need that resource for a higher priority process, give it back to me. That cannot happen, which is why it is called no preemption condition. So only after the process has completed that task, then it will voluntarily give up the resource for it to be assigned to some other process. Again, no preemption is also a condition which will increase the chances of the deadlock state. Now, these three are classified as an indirect deadlock condition. They are going to be slightly different from the fourth one over here, circular wait. It is a direct way to comment about whether we have a deadlock or not. We still have to verify a few things, but this is classified as a direct condition. What is a circular wait? Well, there exists a set of P0, P1, P2, so on up to Pn. These are the processes of waiting processes such that process P0 is waiting for a resource that is held by P1, P1 is waiting for a resource that is held by P2, and so on until the last resource there, Pn-1, so the n-1th process is waiting for a resource that is held by Pn, the last process. And Pn, to complete the cycle, is waiting for a resource that is held by P0. So that particular circular wait is going to increase the chances of a deadlock. Again, this is not guaranteed, but this is a very good chance. It will increase the chance for a deadlock to happen. So we'll take a look at a lot of examples here where we will see that having a cycle may or may not end up in a deadlock state. So 4 conditions, and we talked about how they relate to the deadlock. 3 of them indirect, the last one being direct. And all 4 of them have to be true in order for us to say for sure whether there is a deadlock going to happen or not. Now let's start talking about resource allocation graph, or RAGs. These are going to be graphs that are very easily read, and they give us a graphical interpretation of the state of the system so that we can comment about whether there is a deadlock that may happen or there's no deadlock that can happen. So in this RAG, resource allocation graph, we are going to consider vertices and edges. We are going to use a set of vertices V and a set of edges E. Vertices in a graph are also called nodes, they are also called points. And edges are sometimes called links or lines or arcs. So there will be a bunch of vertices that are connected with each other with edges. That's essentially it. V is partitioned into 2 types of vertices. We have certain processes that can be vertices or resources that can be vertices. So process vertex, it could be the set consists of all the processes in the system. So P1, P2, P3, all these are vertices that are essentially processes in the system, and they belong to one set. We are calling that P. They are again vertices in the graph. Resource R, there is another, that's the second type, and that's a set consisting of all the resource types. These are not resource instances, these are resource types in that system. So R1, R2, R3, and so on. So we have vertices that could be either processes or resource types. And So those are your vertices or nodes or points. Now how about the edges or links or lines or arcs? There could be two different types of edges. Both of them are directed edges, which means that there is an arrow and there is a flow of control from one to the other. A request edge is essentially a process I requesting for a resource type J. So Pi to Rj. So when the directed edge points from a process to the resource, it's a request edge because all a process can do is request for a resource. The other type of edge is called the assignment edge or the allocation edge. It is also a directed edge, but it is pointing the other way. So Rj, the jth resource type, is assigned or allocated to the ith process. So it points from the resource type to the process. Both of them directed. So all we have is a graph of vertices that are interconnected using directed edges. So in order to make things clear and easily understood, we will take a look at how we are indicating a process, how we are indicating a resource, a request edge and an assignment edge. So a process is indicated in the resource allocation graph by simply using a circle. This is going to be a vertex, a process vertex. The resource type with 4 instances, for example, is indicated by a box. It is a node or a vertex, but over here we are showing this as 4 instances of a certain resource type. So the 4 instances are indicated by the 4 gray boxes inside the big square. Now in certain textbooks you might find them to be circles. It doesn't really matter. We are just using gray boxes to represent instances of a resource type. So over here we have 4 instances of a particular resource type here. This is also a resource vertex. Next we have the request edge. So when ith process requests an instance of jth resource type, then we draw the request edge from the process to the particular resource type. In this case, the jth resource type. So the process, the request edge goes from the process anywhere to the resource type anywhere. Now, on the other hand, if Pi, the ith process, is holding an instance of the jth resource type, then the assignment edge or the allocation edge will be pointing in the other direction. But now we are going to start it from a particular instance of the resource and go to the process. So it points from the instance to the process. Notice over here, I am waiting for a resource instance. Over here, I have already assigned the instance of this resource type to the process. So it is allocated, it is still waiting or requesting. So here is an example of a resource allocation graph, and let's see how we can go through and make some conclusions here. So let's start with P1. P1 is requesting for an instance of R1 resource type. However, R1 has only one instance of that particular resource type, which has already been assigned to process 2, P2. P2 is waiting for a resource type R3. There is one instance of a resource type R3 which has already been assigned to P3. And similarly, you can see here for resource type 2, we have assigned or allocated both the instances, one to P2 and one to P1. Now let us see what can happen here. Let's see if there is a cycle. So if we start tracing for P1, I go, yes, there is a cycle, no, there is no cycle. See, they are all directed edges, but there is no complete cycle. Everything is open. So the chances in this case is that there is no deadlock that is going to happen. Now, essentially, how will the system progress? Well, P3 because it has already been assigned R3, P3 can finish. Once it finishes, R3, this particular instance of R3 will be available that P2 can use. P2 already has this resource type, and that resource type just got available. So P2 can finish, and once P2 finishes, P1 already has this instance of R2. It Once P2 finishes, it will release this particular instance of R1. So now P1 can finish. So all three processes were able to finish in this case. So the system was able to make progress and was not in the deadlock state. Now let's take a look at a slightly different resource allocation graph. We have adjusted the graph a little bit. There is also a resource type 4 here with 3 instances of that particular resource type. This is not playing a role in this one, but we just wanted to show how it looks. So the first thing that I would like to try to figure out is whether there is a cycle here, where if I start from P1, yes, 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 yes. So as you can see, there is a cycle, complete cycle is present. And that indicates that there is a deadlock. Now, this is definitely the case over here. The reason is all the resource types, all the resource instances are in demand. So there is one key difference over here. The difference is when you have resource types with only one instance and you have a cycle, then the deadlock state is guaranteed. However, when you have multiple resource types, multiple instances of a resource type, then deadlock may or may not happen. In this particular case, it does, because all the instances of the resource type are in demand. So one is waiting on the other and the other and the other. So there is a deadlock present here. However, I will show you some examples later on where even though there is a cycle, there is no deadlock. Like here. So as you can see here, if I start again from P1, go up, it is requesting for a resource type 1. The two instances, one of the instance of R1 is assigned to P2, the other instance of R1 is assigned to P3. So the cycle goes this way, down to P3, down to R2, down to P1 and back. So there is a cycle. However, because we have multiple instances of a particular resource, we will be able to make progress. Now let's try to see how will the progress be made. So because P2 only needs one resource, R1, and the instance of the R1 has already been assigned to it, then P2 can finish. And similarly, P4 already has been assigned an instance of R2. So P4 can finish. Once P4 and P2 finishes, then it will free up the resource type 1, instance of resource type 1 here, and instance of resource type 2 here. So then P1 can use that particular resource type. P3 already has this guy. It was waiting for another one. It can get it now because P4 is finished. And P1 already has this, it already got that one once P2 finished. So all the processes will be able to make progress, and even though we have a cycle, just because we have instances, multiple instances, several instances of a resource type, we are able to stay away from that deadlock state. So with this, we can summarize that discussion into these statements. 1, if the graph contains no cycles, then there is no deadlock. I don't need to do any more check. Next, if the graph contains a cycle, maybe more, but if it contains a cycle, then two things can happen. 1, if there is only one instance per resource type, that means mutually exclusive condition is being true, only one resource per process, then we have deadlock because there is a cycle and there is only one instance per resource type. The other case is If there are several instances per resource type, then there is a possibility of a deadlock, which means we have to go in and dig a little bit deeper and try to figure out whether the deadlock is going to happen or not. But there is a possibility in that case, not for sure. Okay, so for this particular part, I think that is enough. In the next one, we will talk about how we handle deadlock situations.